But the last day, 4.8, the last section of the chapter, I believe, I don't think I missed anything. Let me just check. Yeah. Application, so word problems. So we already did a little bit of angle of elevation. So this one would be from a point on a level ground. There's my ground. Here's my point. That's 125 feet from the base of the tower. There's my tower. The angle of elevation is 57.2. So this just puts us, and it's degrees. So I have to go back and remember if there's a calculator section or if things are left in terms of the sine, cosine, and tangent. I'll tell you what I mean by that when we finish this one. But approximate the height of the tower to the nearest foot. So if we're looking for the height, we're looking for this, and is this a sine, cosine, or tangent function? Tangent. So tangent of your angle equals opposite over adjacent. And in order to avoid having to use the calculator, sometimes the final answers are just left as 125 times the tangent of 57.2 degrees. So if you don't have a calculator, that would be the best you could do. If you do have a calculator, you also have to know how to use it in the sense of, should we be in degrees, should we be in radians, and you have to flip back and forth frequently in this chapter. So this one, because it's in degrees, your mode goes in degrees. 125 times the tangent of 57.2. Oh boy, I put that in y equals. There we are. And they want it to the nearest foot, so 194 feet. So nothing new there. We already did like angle of elevation and depression in a different section. But these will get more tricky. I'm going to start small. Okay. We're taking our first hot air balloon ride. Anybody ever been in a hot air balloon? Nobody? And would anybody want to go? Like if they were giving free hot air balloon rides outside, who would not go? A couple of you. Yeah, it's a little unnerving because like what if something happened? All right. Your friend is standing on level ground 100 feet away from your launch. We'll call this my launch. This is friend. At one instant, the angle of elevation from your friend to you. So you're going to kind of keep going up. You're launching. So at one instant, the angle of elevation is 31.7 degrees. 1 minute later, the angle of elevation is now 76.2. So 1 minute later, when you're even higher, can you guys see how that angle of elevation would grow as the person goes up? So that bigger angle of elevation is 76.2. How far did you travel to the nearest tenth of a foot? So how far you traveled is right there. Here's where you were. Here's where you now are. That's how far you traveled. That little segment, though, is not in a right triangle. It's a part of a leg of a right triangle. So what would be an appropriate game plan? Who can offer up some advice? Find the length of that segment. Olivia? Right. So find the entire length using your 76.2. So we can call that, like, let's call that y. Because that is part of a right triangle. And find the smaller length of it. We can call that x, because that is a part of a right triangle, and then the difference between them will be the distance that was traveled. So if I find y first, that would be the tangent of 76.2 equals y over 100. And then to find x, I would do the tangent of 31.7 equals x over 100. Find each of those. So y equals 100 times the tangent of 76.2, which is 407.127. X is 100 times the tangent of 31.7, which is 61.76. That seems like a lot. And then the difference between them. .345. Here's 1/10 of a foot. I get 0.4. I think it seems like a lot because I don't think I didn't draw my graph to scale, right? Couple things that play in there is, number one, if you increase an angle of elevation by 1 degree, that 1 degree isn't going to make that much of a difference if it's not very far away. But the further away it is, like if that leg was that much longer, 1 degree of a difference makes more of a difference the further out you get. So part of what's playing into that is how far away this is. The other part that actually does make more sense is I over doubled the angle, 31.7 to 76.2. That more than doubled, but my picture did not really represent that well. So I think it's my picture is misleading. So do you remember bearing? Did we do bearing already with flying airplanes? I think we did. Like pilots flying in a certain bearing. Does that sound familiar to anybody? Oh, I get it confused. Year to year, class to class. Okay. So a boat leaves the entrance to a harbor. Here's the harbor. And travels 25 miles on a bearing of north 42 degrees east. So in aviation, in boating, when you're out in the middle of the ocean or you're in the middle of the sky and you have no frame of reference for direction, north is 0 degrees. Due north is 0 degrees. And then it just goes around the circle. So if you're flying at a bearing of 90 degrees, you're flying that way. 180 would be due south. 270 would be kind of like equate that to a compass, north, south, east, west, where due north is 0 and then you go around. Sometimes they will only talk about the angle between 0 and 90, but they'll give you the directionals based on this. So in this case, this 25 miles that this person is traveling north, we'll just do north, south, east, west. Northeast at 42 degrees. This is what's 42 degrees. So it's always the number relative to like the vertical axis, the 0 degree line. So they went on that for 25 miles. The captain then turns the boat clockwise. So if you're going like this, what's clockwise? Turning left or right? Right. He turns it 90 degrees. So there's your right triangle. And travels 18 miles on a bearing of south 48 degrees east, which actually should make sense because your bearing is relative to a vertical, right? And if he's going southeast, we all can agree that that's southeast relative to this north barrier, and this is 48 degrees in the southeast direction, which should make sense because think about your Z from parallel lines. I actually didn't need to give you that 48 because this 42 Z with parallel lines, that would be 42, and they already told you the 90 degrees, so 42 plus what would make 90, but just showing you that kind of makes it all come together. So that 90 degree makes sense, and they gave you the bearing on top of it. Does that make sense? Does anybody know a pilot? Yeah? Could you ask him for me? Alex Battershell he used to fly planes at the Hamburg airport. So he was my guy. He knew more about this than I. Can you ask them if they would say flying at a bearing of south 48, you're going to have to write this down, or you can go back to the video. Would they, and maybe they don't practically say any of this, but at some point he would know what this means. South 48 degrees east, or do you say 0, 90, and that's 48 and that's 42. Would he do 90 plus 42 and just not use the directional and just say at a bearing of 90 plus 42, 132? Do you know what I'm saying? Like, would he call that a 48 degree angle and give the direction? Or would he just call it 132 degrees, which kind of gives you the direction without having to say it? I need to know this. I can't remember what Alex Battershell told me years ago. So I need a refresher. Okay, thank you. All right, so anyway, we have our picture. 18 miles going that way. How far is the boat from its harbor entrance? So you're essentially finding that length. How would you go about doing that? Bridget, what method would you use? So which angle is your 42 degree angle of this triangle? This angle? Yeah, you're right. So that's 42, that's 48, which means that's 42. So you would do the cosine of 42 equals what over what? Adjacent over hypotenuse. Would anybody use something different? Olivia? You could just do Pythagorean theorem, right? I'm not surprised that, Bridget, you were in that frame of mind because our other problems were SOHCAHTOA. But when you have two sides, you can just do the Pythagorean theorem, 18 squared plus 25 squared equals hypotenuse squared. You know, I'm not going to finish that one out. Okay. So simple harmonic motion is things that move with that wave-like behavior, so they associate with the sine and cosine curves pretty well. They don't typically have a shift of any sort, so there's an amplitude that plays a role, and there's also a horizontal stretch or compression based on the length of the period being changed. So in this particular example, and you have to read into whether it fits the cosine or sine model is really what we're after. A ball on a spring is pulled 4 inches below its rest position and then released. So picture obviously the spring going back and forth. The period of the motion is 6 seconds. Write the equation for the ball's simple harmonic motion. So based on this scenario with the ball being pulled 4 inches below its rest position and then released. So when it's released, that starts the activity. Would this be a sine or a cosine? Mitch. Cosine. So I tend to visually think of a graph. It's starting 4 below, and then it's released, and it's, you know, it's starting overstretched, so then it's going to compress and do that. Right? Does that make sense? So -4 to 4, and then it tells us that the period is 6 seconds, so we can just scale our x-axis to fit that. So now if we are using the cosine function, we have d equals, what is our a value? Ada, what do you think? Anybody think anything different? Connor? -4. You see why? Because positive cosine curves go from maximum to maximum, and this is a negative cosine curve. So your A is actually -4. If I had said what's the amplitude, 4 would be the amplitude. But what's the A value? The A value is -4. And then this Greek letter, which I can't even remember what it is. Does anyone know what that is? A little lowercase w. It's some Greek letter. That's like your B. That's no different than our B has been typically. So we want to figure out what that is. So figure out W, and there's your period right there. 2 pi over that W is supposed to equal what? Yep. Yes, 6 seconds, good. So solve for that. Divide by 6, and that equals pi over 3. Nothing new there, just different variables, just because it's this simple harmonic motion. Probably comes from physics, to be honest with you. And then in 5, again with a simple harmonic motion, they're giving us a mass on a smooth table is attached to a spring. The mass moves in simple harmonic motion. And here is our equation. Find the maximum displacement, the frequency, and the time required for one cycle. So the maximum displacement is your amplitude, and that is 10. The time required for one cycle is your period. So period equals 2 pi over, and our B value, or our W value in this case, is pi over 6. So most of us would probably keep, change, flip. Pi's cancel. 12 seconds. And I don't talk much about frequency, because frequency is one of those funny things where it depends on what type of problem you're doing. So if it's a sine or cosine function that has no meaning attached to it, it's how many cycles you can fit in within the span of 2 pi, essentially. But that's not the overall definition. That's just what we assume it is if we're dealing with a sine or cosine function. So that's why last year you guys used to look at this number, and that was the frequency. But the frequency is the number of cycles per kind of unit that you're working in. And because our time is in seconds, this would be how many cycles can you fit in 1 second? You wouldn't say how many cycles can you fit in 2 pi here because it's not the context of the problem. Your x-axis is labeled based on seconds. So how many cycles fit in one of those units? If 1 cycle, and we're doing a positive cosine, so 1 cycle takes 12 seconds. So how many cycles fit in 1 second? Andrew, 1/12. Does that make sense? 1/12 of a cycle. The frequency to me is always just the reciprocal of your period. Whatever your period is, the frequency is just the reciprocal of that.